Now I'm going to combine mental math with paper. I'll ask you to give me a 3-digit number.
367.
367 times another 3-digit number.
896.
896. Okay, here we go. Is it 328,832?
Yes.
Great. Here, let's try a 4-digit number.
7,172.
7172 times another 4-digit number.
2,345.
Okay, here we go. $16,818,340?
Exactly.
Good. Although the focus of this course is on doing math in your head, often problems are presented to you on paper. For instance, when you're given a column of numbers to add up or when balancing your checkbook. I will show you in this lecture some techniques you can use to speed up calculations that are performed on paper using methods that are seldom taught in school. I'll also give you some interesting ways to check your answer. We'll still be doing some mental math along the way, but we'll take advantage of the fact that we now have paper, so we won't have to worry about remembering the problem. Let's start by adding columns of numbers. You might find yourself doing this if you were adding a list of all your charitable donations for the year or determining your portion of the phone bill. I'll just do one example since it's probably similar to the way that you already add columns of numbers. Now here are some numbers from a recent credit card statement. Now in this course, when doing mental math, I emphasize doing all calculations from left to right. But when we do the problem on paper, I usually prefer to do it from right to left, like we're taught in school. The reason for that is it's easier to keep your columns lined up, and you don't have to worry about having to erase any numbers that you've written down because of carrying. With practice, anyone can get fast at this skill. Okay, so when adding a column of numbers, just say the running total like so. All right, so we'll start on the right with 6 plus 0 is 6, plus 5 is 11, plus 5 is 16, plus another 2 is 18. So we put down the 8, carry the 1. The next column would go 1, 6, 11, 20, 29, 34. Put down the 4, carry the 3, and so on. Maybe the most important lesson to learn here is that you can check your answer by adding the numbers from bottom to top. So if you made any mistakes the first way, you probably won't make the same mistake again. If you get the same answer each way, then your answer is probably right. As for doing subtraction on paper, I have a lot of experience doing that several times a week in my checkbook. The main thing I want to show you here is a different way to use complements. Okay, so here we're starting with a balance of $1,235.79, and we have to subtract $271.82. Now, when doing checkbook math, I always first do the cents and then do the dollars. Okay, so I have to subtract 79 minus 82. Now, if the problem were 82 minus 79, then of course that would be 3 cents. But since it's 79 minus 82, we take the complement of 3 cents, which is 97 cents. So we write down 97 cents. Next, we need to subtract 272. How are we going to do that? Well, because we've got the number 1,235, we'll subtract 272 by subtracting 300, then adding back its complement, which is 28. Okay, so 1235 minus 300 is going to be 935, and then we're going to add back 28. 935 plus 28 is 963, and there's the dollars. Okay, next we have to subtract $375.91. So first we'll do the cents. This time it's easy. 97 minus 91 is 6 cents. I had a 6 cents about that answer. Next we're going to take 963 minus 375. How are we going to do that? There are actually two ways of doing this problem using complements. Let me show you both of them. So the normal way is you'd say, well, let's see, 963 minus 375. I'll subtract 400 and add back 25. 963 minus 400 is 563. When you add back 25, you have 588. Here's another way of doing it. I look at 963 minus 375. I know that the answer is going to be below 600, right? Because 75 is bigger than 63. So I'm going to subtract 400 right away and say, okay, it's 500 and something. It's in the 500s. I'll write the 5 down. Now, if the problem were, now I have to do 63 minus 75. Now, if the problem were 75 minus 63, it would be 12. But since it's 63 minus 75, it's the complement of 12, which is 88. So there's the rest of our answer, $588 to go along with the 6 cents. You can check your work by working backwards, turning a subtraction problem into an addition problem. Now, even if you haven't been balancing your checkbook, you might now want to start. It's a great way to become more comfortable with numbers, and you'll understand exactly what's happening with your money. Now here's a fun way to multiply numbers of any length together. You just write down the answer from right to left. It almost looks magical. I call it the crisscross method, although it goes by other names such as cross multiplication, polynomial multiplication, and Vedic multiplication. Let's start with a 2-digit by 2-digit problem, 67 times 83. Okay, first, we multiply the digits on the right. We do 7 times 3, which is 21. We put down the 1, we write down the 1, and we carry the 2. Okay, now we do the crisscross step. I'll do it slowly. We do 3 times 6, which is 18, and we do 8 times 7, which is 56. We'll add the 2 that we carried, plus 18 plus 56 to get 76. Now, when I'm doing this in my head, here's what I do. I have that 2 that I've carried. I do 3 times 6 to get 18, and then I'll add those together. 18 plus 2 is 20. Then I'll do 7 times 8, 56. 20 plus 56 is 76. So what do we do with the 76? We put down the 6, we write it down, and we mentally carry the 7. Finally, we do 6 times 8, which is 48. Add that to the 7, giving us 55, and there's the answer, 5561, 5,561. Here, let's try another example. Let's do 2358, 23 times 58. We start with 3 times 8, which is 24. So we put down the 4 and we mentally carry the 2. Next we do a crisscross, right? We do 8 times 2, which is 16. 5 times 3 is 15. Let's add those all together. So we've carried the 2. 8 times 2 is 16. Add that to 2 is 18. Plus 15 gives us 33. So we put down the 3 and we carry the 3. Finally, we do 2 times 5, which is 10. Add that to the carried 3, 13, and write that down. There's your answer, 1334. So why does this work? It's really just the distributive law. The problem 23 times 58 is 20 plus 3 times 50 plus 8. And that has 4 separate components. There's 20 times 50, 20 times 8, 3 times 50, and 3 times 8. The 3 times 8 we do at the beginning. The 20 times 50 we do at the end. That's the 2 times 5 times 100. And then the 20 times 8 and 3 times 50, that's the same as 2 times 8 plus 3 times 5 multiplied by 10. That was our crisscross step. If we extend this logic, we can do 3 by 3 multiplication or even higher. Here, if we took the pi problem, 314 times 159, the traditional pencil and paper method would look like this. But with the crisscross method, instead, it goes like this. We start on the right with 4 times 9, which is 36. So we put down the 6, mentally carry the 3. Okay? Next we do our first crisscross. We do 9 times 1, which is 9. Add that to the 3, which is 12. Then 4 times 5 is 20. 12 plus 20 is 32. You put down the 2, carry the 3. Now what comes next? What comes next is a triple cross. This is the hardest part. All right, you still got that 3 that you've carried. We do 9 times 3, we'll do 4 times 1, and we'll do 5 times 1. Add those all together with the 3 for the next digit. Okay, so I'm holding on to the 3. 9 times 3 is 27, plus the 3 is 30. 1 times 4 is 4, that's 34. Plus 5 times 1, 5. 34 plus 5 is 39. Take a breath, put down the 9, carry the 3. Okay? Next you do a double cross. We do 5 times 3 and 1 times 1. We've got 3 plus 15 plus 1. That's 19. I put down the 9, carry the 1. And finally, we do 3 times 1, which is 3. Add that to the 1 to get 4. And there's your answer, 49,926. Notice that you only ever wrote down the answer. No other partial results were written. Also notice that this calculation takes 5 steps. The first step has 1 multiplication. The next step has 2 multiplications. Then 3 multiplications. And then we're down to 2. And then down to 1. Also notice that in this process, every digit on top at some point gets multiplied by every digit on the bottom. A 4 by 4 calculation would require 7 steps. In the first step, we have 1, and then a crisscross of 2, then a triple cross of 3. The fourth step has 4 multiplications, and then it gets easier. The fifth step has 3, and the sixth step has 2, and the seventh step has 1. The crisscross method can also be used when the number of digits are different. Like here, if I had this 4-digit number times this 3-digit number, it can easily be turned into a 4-digit times 4-digit problem as well. By the way, the crisscross method has been around for a very long time. The method was first described in the book Liber Abaci, written in 1202 by one of my favorite mathematicians, Leonardo of Pisa, also known as Fibonacci. Now, we've seen how to check our answers to addition and subtraction problems. How can we check the answer to a multiplication problem? What I usually do is something called the digit sum check. Although it's not foolproof, it's very simple to do. Let's take our earlier problem, 314 times 159, and check the answer by digit sum. What do? We take the answer and we sum the digits. 4 plus 9 plus 9 plus 2 plus 6, if we add those together, we get 30. That's a 2-digit number, so let's add those digits. 3 plus 0 is 3, so our answer is said to reduce to the number 3. Now, let's reduce the original numbers. 314, if I sum those digits, we get 8. And 1 plus 5 plus 9 is 15, and 15 reduces to 6. And since this was a multiplication problem, I'm now going to multiply the reduced numbers. 8 times 6 is 48. That's a two-digit number, so I'll reduce it to 12. And the 12, I'll reduce that to 3. Now check this out. We've got 3 for our answer. We have 3 for the smaller problem. Those 3's match. And that is not a coincidence. If all of your calculations are correct, then these numbers have to match. Now, as a word of caution, just because the numbers match doesn't mean that your answer is right. But errors are caught by this method about 90% of the time. On the other hand, if the numbers don't match, then you've definitely made a calculation error somewhere. This method is also known as casting out nines. The reason it's called casting out nines is that when you reduce a number by summing its digits, the number you end up with is its remainder when divided by 9. So look at the number 67. Its digits add up to 13, and 13's digits add up to 4. Now, if you took the original number 67 and divided it by 9, you'd get 7 with a remainder of 4, that same 4. Or take 83. Its digits add up to 11, and 11's digits add up to 2. If you divide 83 by 9, you get 9 with a remainder of 2. Not a coincidence. And when you multiply something with a remainder of 4 times something with a remainder of 2, you have to get something with a remainder of 8. And sure enough, 5561, when you add up its digits, you get 17, which reduces to 8. Casting out nines works for addition and subtraction problems too, even with decimals. Here was the column of numbers that we added earlier. All right, now if we ignore the decimal point, look at the answer, 39848. If we add up those digits, we get 32, and 32 reduces to 5. Okay, now let's check our work by summing the digits of each entry, and we'll ignore the decimal point. We can also ignore the digit 9, since the 9s are being cast out anyway. Okay, so we've got 11256. That's our first number. Those digits add up to 15, and 15 reduces to 6. Now then we have 9650. Oops, ignore that 9. 650 adds up to 11, and 11 reduces to 2. Then 1 plus 4 plus 5 is 10, which reduces to 1. 4 plus 8 plus 5 is 17, reduces to 8. 1 plus 8 is 9. You can even let that 9 reduce to 0. You could cast out that 9. 1752 adds up to 15, which reduces to 6. And now when we add those one-digit numbers, 621806, those add up to 23, and 23 reduces to 5, which is exactly the number we were hoping for. Casting out nines works for subtraction problems too. If the subtraction results in a negative number, then just add 9 to the answer. So for example, the problem 1, 2, 3, 5, 8, 13. I'm sorry, 1, 2, 3, 5 minus 8, 13 is 422, and 422 reduces to 8. Now let's check that. 1, 2, 3, 5 adds up to 11, which reduces to 2, and 8, 13 adds up to 12, which reduces to 3. And since this is a subtraction problem, we do 2 minus 3 is negative 1. When we see a negative number, we don't panic. We just add 9 to it. This is casting out nines anyway, so we're going to add 9 to it to get 8, and those 8s match, so we're happy. Here's a problem that could appear on a standardized test that does not allow calculators. Which of these numbers has a square of 3,364? In other words, find the square root of 3364. Here are 5 possibilities. Now, we can eliminate some of them right off the bat. For instance, we know that 50 squared is 2,500. So if the square is going to be 3364, our original number is going to have to be bigger than 50, so that eliminates choice A. And 60 squared is 3,600, which is larger than 3364, so the answer has to be smaller than 60, so that eliminates choice E. And the answer can't be 56 because 56 times 56, we know that ends in the number 6, right? Even the crisscross method would tell you that. So see you later, C is not a possibility. So now the possibility, it's either B or D. The last digit of B is 2. 2 times 2 is 4. Last digit of D is 8. 8 times 8 ends in 4. So which of those two is it going to be, B or D? Well, there are two ways to figure out which one. Do you remember from the first lecture how to square numbers that end in 5? Like 55 squared is what? We do 5 times 6 is 30, attach the 25 to get 3,025. So 55 times itself is 3,025, so the answer has to be bigger than 55. So B is gone. Be gone, B. We're left with the answer D, 58. Here's another way to eliminate choice B through casting out 9s. Can 52 times 52 equal 3364? Well, let's see. 52 reduces to 7. 52 reduces to 7. And since it's a multiplication problem, I'll do 7 times 7 to get 49, which reduces to 13, and that reduces to 4. All right, now let's see what our answer, 3364, looks like. 3364 adds up to 16, and 16 reduces to 7. 7 and 4 don't match. So 52 times 52 can't be 3364, so that allows us to eliminate 52 as a possibility. On the other hand, you might want to, for extra assurance, check the number 58. 58 reduces to 4, and 4 times 4 is 16, and 16 reduces to 7, so there we do have a match. So casting out 9s confirms your answers. I've always felt that the number 9 was a magical number because of its simple multiplication table, its divisibility test, and the casting out 9s process. In fact, there's even a magical way to divide numbers by 9 using a process called Vedic division. If you have paper available, this process is way faster than doing the division by the traditional method. Now, I'll give more details about Vedic division in Lecture 8, but let's see how it divides numbers by 9, just to whet your appetite. Consider the problem 12302 divided by 9. Now, if you did this by traditional long division, the solution would look like this. Okay? Here's the Vedic method. We started with 1. The first digit is 1, so we bring the 1 up. Next, we add 1 plus 2, which is 3. Then 3 plus 3 is 6. Then 6 plus 0 is 6. And now we're at the last digit. That's our time for the remainder. 6 plus 2 is 8. And believe it or not, that's the answer. 1366 with a remainder of 8. Here, let's do another problem. Let's do the pi problem, 31415 divided by 9. Okay, we start with a 3, so we bring the 3 up. Then we do 3 plus 1, which is 4. Then 4 plus 4 is 8. Then 8 plus 1 is 9. And finally, we're at the remainder step. 9 plus 5 is 14. So your answer is 3489 with a remainder of 14. I'm not going to leave the answer that way. Since our remainder is bigger than 9, we can actually squeeze one more 9 into here. So we can increase 3489 by 1, so it becomes 3490, and then we decrease the remainder by 9, and 14 minus 9 is 5. So there's the answer, 3490 with a remainder of 5. Okay, now you should be able to do the next problem instantly. Try doing 10200304 divided by 9. Here we go. We've got a 1, 1, 3, 3, 6, 6, and 6 plus 4 is 10. There's your answer, 113366 with a remainder of 10. But let's subtract 9 from that remainder to give us 113367 with a remainder of 1. Now, if this process reminds you of how we multiplied by 11s in the first lecture, that's not entirely a coincidence. After all, dividing by 9 is the same as multiplying by 0.111111. Just like with 11s, we need to be able to handle carries when they occur in the middle of the problem. So here's the carry rule. After you carry, just subtract 9, then keep going. You might say, carry on. Okay, so let's look at the problem 4821 divided by 9. All right, we bring the 4 up, and now 4 plus 8 is 12, which is bigger than 9. So we indicate a carry. We put the 1 there to indicate a carry, and then subtract 9. 12 minus 9 is 3, and now you continue as usual. 3 plus 2 is 5, and now you're at your remainder step. 5 plus 1 is 6. And so your answer is, it's not 435 with a remainder of 6, because you've got that 1 carrying. It's 535 with a remainder of 6. Here's a problem with more carries. Let's do 87654 divided by 9. All right, so we bring the 8 up. And now we do 8 plus 7 is 15, carry time. So we indicate, put a 1 above the 8. Then we subtract 9 from our 15 to get 6. Then 6 plus 6 is 12, carry time. Subtract 9 to get 3. 3 plus 5 is 8. And now we're at the last step for the remainder. 8 plus 4 is 12. And there's your answer, 9738 with a remainder of 12. But since 12 is bigger than 9, I'll increase the 9738 to 9739, and the 12 becomes a 3, since 12 minus 9 is 3. So there's the answer, 9739, with a remainder of 3. This is definitely faster than the way you would normally do this on paper. Here's one more example with an especially pretty answer. Let's look at 111111 divided by 9. Okay, so we have, we bring the 1 up, and as we keep adding 1s, we get 1, 2, 3, 4, 5 with a remainder of 6. Check this out. 11 divided by 9 is 1 with a remainder of 2. 111 divided by 9 is 12 with a remainder of 3. Right? The Vedic process gives us 1111 divided by 9 is 123 with a remainder of 4, and so on. Now let me show you one more technique for mental multiplication that's especially well suited for paper. I call it the close together method, and it can be used to multiply any two numbers that are near each other. It's especially impressive when both numbers are near 100. Let's look at the problem 107 times 111. Okay, so first we note how far each number is from 100. 107 is 7 away. 111 is 11 away. Now we add 107 plus 11, or 111 plus 7. Either way, you'll always get the same thing. In this case, that's what? 107 plus 11 is 118. Next, we do 7 times 11, which is 77. Write it down. And that's your answer, 11877, 11,877. Here, let's do another example. Let's do 103 times 106. So 103 is 3 above 100. 106 is 6 above 100. We do 103 plus 6, which is 109. Then we do what? 3 times 6 is 18. And that's the answer, 10,918. Now, if you're interested in why this works, it's based on the algebra z plus a times z plus b is z plus a plus b times z plus ab, where typically Z is an EZ number with zeros in it. Like Z equals 100 is a good number for Z. And A and B are their distances from the EZ number. Okay? So for the problem 103 times 106, Z is 100, and my distances are A equals 3 and B equals 6. So our formula tells us that 100 plus 3 times 100 plus 6 is 100 plus 3 plus 6 times 100 plus 3 times 6. That's 109 times 100 plus 18. That's 10,918, and that was our last calculation. This also works for numbers below 100. Like look at 97 times 94. This time, since 97 is 3 below 100, we indicate that with a -3. And 94 is 6 below 100, so we write down -6. So now you do 97 minus 6 or 94 minus 3. Either way, you'll get 91. Then we do -3 times -6, which is positive 18, and that's the answer, 9118. Now what was really happening was we were really doing 91 times 100 to get 9100. Then we were adding -3 times -6, 18, to get 9118. I say that so you'll better understand this next example. Let's do 103 times 94. This time one number's above 100 and another number's below 100, right? 103 is 3 above, 94 is 6 below. So next you're going to do what? You're going to multiply 100 by what number? Either do 103 minus 6 or 94 plus 3, take your pick. Either way you get 97. Okay? And then we take 3 times -6, which is -18. So what's going on here? Is the answer 97 -18? Well, not quite. It's 97 times 100, 9700. And then we subtract 18 to get what? It's 9600, and the complement of 18 is 82. So there's your answer, 9682. This method can also be applied to any numbers that are close together. Remember in lecture 1 when we multiplied numbers like 17 and 18? That was just a special case of the close together method. Here both numbers were close to 10, right? 17 was 7 above 10, 18 was 8 above 10. We did 17 plus 8, which is 25, multiplied that by 10 to get 250. Added to that, the product of the last digits, 7 times 8, is 56, and there's the answer, 250 plus 56, 306. But you can do that problem another way that you might find easier. Since both numbers are closer to 20 than they are to 10, right? We're dealing with 17 and 18. You could compare both numbers with 20. So 17 is 3 below, 18 is 2 below, 17 minus 2 is 15, and now you multiply that by 20, the number that you were close to. 15 times 20 is 300, and now all you have to add is -3 times -2, 6, to get 306. So you have an easier addition problem. Instead of doing 250 plus 56, you're doing 300 plus 6. Here's another example with numbers that are close to 200. 205 times 212. 205 is 5 above. 212 is 12 above. We do 205 plus 12, which is 217, and we multiply that by 200. Now 217 times 2 is 434, so 217 times 200 would be 43,400. All we add to that is 5 times 12, which is 60, and there's your answer, 43,460. All right, let's do two numbers that are close to 1,000. 997 times 994. If we did this problem the traditional way, it would look like this. not something you're going to want to do in your head. On the other hand, by the method that we just learned, by the close together method, here's how we would do it. We would take 997, that's 3 below 1,000. 994 is 6 below 1,000. Take 997 minus 6 to get 991. Multiply that by 1,000, which is 991,000. Add to that negative 3 times negative 6, which is 18, to get 991,018. Once you know how to do the close together method on paper, it's not too hard to do it all in your head. And I'll show you how to do that in the next lecture. We'll also learn to mentally multiply any two-digit numbers and square numbers at lightning speed. So be there or be squared.